Friends, welcome to the tutorial series on network analysis made simple. During the previous few tutorials, we discussed about the various theorems such as superposition theorem, Thevenin's theorem, Norton's theorem, maximum power transfer theorems and so on. I also suggested to go through my earlier tutorials on Kirchhoff's laws, mesh current method and node voltage method and so on. Friends, these earlier tutorials will help building your confidence in identifying the network connectivity. They also help you to choose proper method of network solving for a network you get. During this tutorial, we shall study reciprocity theorem. Before we start the discussion on reciprocity theorem applied to electrical networks, I wish to brief you about the reciprocity property in general and then take you to the reciprocity theorem. Let me begin with the quote by the famous celebrity Ms. Deepika Padukone. She said, "If two actors have equal creative give and take between them, it translates beautifully on the screen." Yes, friends, it is beautiful. But I am going to talk to you about give and take in electrical networks. Giver could be a source and taker could be a response. Let's go ahead and see. Friends, I said giver could be a source in electrical network. We know sources deliver power, so they can be considered as givers. Response across a branch could be a current or a voltage across the load. The loads absorb or receive power, so they are takers. Friends, reciprocity is a property of a network. It is related to the giver, the source, and the taker, the response. We know giving and taking property is not equal in all stakeholders in general. So also, this reciprocity is not applicable to all electrical networks. But then friends, first we shall see what are the limitations of this reciprocity property as far as the electrical networks are concerned. The first and the foremost is the network should be a single source network. It should contain passive and linear circuit elements. The initial conditions are assumed to be absent. Dependent sources are excluded even if they are linear. So friends, the reciprocity relation holds good for only limited class of linear circuits, and such networks are called as reciprocal networks. To prove the reciprocity theorem for a network, when the source and the response positions are interchanged, the polarity of the source has to be maintained in the same polarity as that in the original network. Friends, this aspect I will clarify when we solve the numerical examples. Then, what is the reciprocity principle? Friends, the principle in its simplest form can be stated as the property in which the ratio of the source and the response remains constant even after the exchange of the positions of the source and the response. So, in view of the above, the reciprocity theorem can be stated as: in a single source linear and bilateral network, the ratio of source and the response remains constant even when the positions of the source and the responses are interchanged. Friends, though the reciprocity theorem has limitations, its applications are used in different situations, such as reciprocity principle serves as a basis for proofs of various aspects in electromagnetic systems, such as symmetry in Green's functions, scattering matrix formulation of microwave networks, propagating modes in waveguide structures, and identical reception and radiation property of antennas. Friends, though the reciprocity property is applied in many situations as mentioned, in this tutorial the discussion is limited to simple electrical networks to the extent of understanding the principle of reciprocity theorem. we shall see in the next discussion. Friends, now let me illustrate the procedure to apply and prove the reciprocity theorem for an electrical network. First, given a single source linear and bilateral network, find the response in the branch asked for using suitable network solving technique. Say the response found is the current Ix in that branch. Then, introduce the source in the branch where the response was found. Keep the polarity of the source same as earlier and force the source in the original branch to 0. Now, apply suitable network solving technique and find the current Iy in the original branch, and if the network is reciprocal, then Ix will be equal to Iy. Friends, now we are ready to solve a numerical example wherein we are required to find Ix in the circuit shown and prove the reciprocity theorem. The strategy I have already illustrated. To find Ix, consider the network shown in figure 2. Hope you clearly visualize 3 independent loops. Hence, mesh currents I1, I2 and I3 are assumed as shown. By writing the Kirchhoff's voltage equation for loop 1, we get 10 I1 minus 8 I2 minus 2 I3 is equal to 10. Similarly, for loop 2, we get minus 8 I1 plus 22 I2 minus 10 I3 is equal to 0. Similarly, for loop 3, we get minus 2 I1 minus 10 I2 plus 18 I3 is equal to 0. By solving the 3 simultaneous equations, we get I1 is equal to 2.11428 amperes, I2 is equal to 1.171428 amperes and I3 is equal to 0.8857 amperes. But friends, Ix is equal to I2 minus I3. So, by substituting the values, we get Ix is equal to 0.2857 amperes. Now friends, we arrive at a strategic point. Hence, I suggest you understand it clearly and carefully. If you remember, we found Ix in the branch containing 10 ohm resistance and the answer for Ix we got is positive. So, it flows from the top to bottom as shown. So, now we have to introduce the source of 10 volts in the branch containing 10 ohm such that it drives the current in that branch from top to bottom. So, the polarity of the source introduced has to be positive at the bottom and negative at the top as shown. Next, the source of 10 volts in the original branch should be forced to 0 by short circuiting it as shown. Further, note that the current I1 in the original branch is positive, hence the direction of the current I1 through the source is from the right to left. So, the direction of Iy in the changed circuit also should be from right to left as shown. These points are very important, friends. Hence, I suggest you pause the video for a moment, think and understand these aspects clearly. Next is routine, friends. 3 mesh currents I1, I2 and I3 are assumed as usual. By writing the Kirchhoff's voltage equation for loop 1, we get 10 I1 minus 8 I2 minus 2 I3 is equal to 0. Similarly, for loop 2, we get minus 8 I1 plus 22 I2 minus 10 I3 is equal to 10. And for loop 3, we get minus 2 I1 minus 10 I2 plus 18 I3 is equal to minus 10. Friends, by solving the 3 simultaneous balance equations, we get I1 is equal to 0.2857 amperes and I2 is equal to 0.42857 amperes and I3 is equal to minus 0.2857 amperes. But IY is equal to I1 and that is equal to 0.2857 amperes. We have got it. So, friends, since Ix is equal to Iy is equal to 0.2857 amperes, the reciprocity theorem is proved. Friends, now let us consider another example to verify the reciprocity theorem for the network shown in figure. We are required to find Vx, for which we need to find Ix in that branch. If you observe the network, you find that a current source of 5 angle 90 amperes is directly connected across two parallel branches, one of 5 plus J5 and the other of 2 minus J2 as shown. So, to find Ix, we can easily opt for the current division theorem. Hence, Ix is equal to impedance of the other branch divided by sum of the two parallel branch impedances into the total current. By solving it, we get Ix is equal to 4.642 angle 111.8 amperes, but Vx is equal to Ix into minus J2. By substituting the values, we get Vx is equal to 9.284 angle 21.8 volts. This is simple, friends, but now we arrive at the critical juncture of exchanging the source and the response. We found Vx, which was the voltage across minus J2. We have to introduce the current source of 5 angle 90 amperes across minus J2 such that the polarity is maintained as in the original network. Observe the polarity of Vx, which is directed upwards. So, for the current source that we introduce should also drive the power as in the original network, for which the direction of the arrowhead should have to be same as Vx. Note that. Further, to make 5 angle 90 ampere source in the original branch 0, we have to open circuit it as shown. Also, the polarity of Vy has to be in the same direction as the arrowhead in the original network. Note that. Having done this carefully, the next is routine, friends. Note the branch containing voltage Vy is open. So, the two parallel branches across the current source now are one of minus J2 and the other of 2 plus 5 plus J5. To find Vy, we have to find Iy and note Vy is equal to Iy into 5 plus J5. So, Iy is equal to impedance of the other branch divided by sum of the two parallel branch impedances into the total current. By solving it, we get Iy is equal to 1.313 angle minus 23.2 amperes. But we know Vy is equal to Iy into 5 plus J5. By substituting the values, we get Vy is equal to 9.284 angle 21.8 volts. So, we find that Vx is equal to Vy is equal to 9.284 angle 21.8 volts. Hence, the reciprocity theorem is verified. Friends, next consider the network shown in figure to find Ix and to verify the reciprocity theorem. To find Ix in the given network, you find that the network contains 3 junction nodes 1, 2 and 3. Considering the third node as a reference, let V1 and V2 be the unknown junction voltages of node 1 and node 2 respectively. By writing the Kirchhoff's nodal equation for node 1, we get V1 minus 100 divided by 3 plus V1 divided by 14 plus V1 minus V2 divided by 12 is equal to 0. By rearranging and solving, we get 41 V1 minus 7 V2 is equal to 2800. Let it be equation 1. Similarly, for node 2, we get V2 minus V1 divided by 12 plus V2 by 4 plus V2 by 4 is equal to 0. By rearranging and solving it, we get minus V1 plus 7 V2 is equal to 0. Let it be equation 2. By solving the simultaneous balance equations 1 and 2, we get V1 is equal to 70 volts and V2 is equal to 10 volts. But Ix is equal to V2 divided by 4. By substituting for V2, we get Ix equal to 2.5 amperes. Now, to exchange the source and the response, note the source of 100 volts is introduced in the branch such that it drives the current in the same direction as Ix. Further, 100 volt source in the original branch is made 0 by short circuiting it. Note the response Iy is directed in the same direction of current delivered by that source of 100 volts. Friends, next is routine. Let V1 and V2 be the junction node voltages as assumed earlier. By writing the Kirchhoff's nodal equation for node 1, we get V1 by 3 plus V1 by 14 plus V1 minus V2 by 12 is equal to 0. By rearranging and solving, we get 41 V1 minus 7 V2 is equal to 0. Let it be equation 1. Similarly, for node 2, we get V2 minus V1 by 12 plus V2 by 4 plus V2 plus 100 by 4 is equal to 0. By rearranging and solving it, we get minus V1 plus 7 V2 is equal to minus 300. Let it be equation 2. By solving the simultaneous equations 1 and 2, we get V1 is equal to minus 7.5 volts and V2 is equal to minus 43.92 volts. Note the current V1 by 3 in this equation flows away from the junction node 1, but Iy is equal to minus V1 divided by 3, and that is equal to minus of minus 7.5 divided by 3, which will give us Iy is equal to 2.5 amperes. So, friends, we find that Ix is equal to Iy is equal to 2.5 amperes, and hence the reciprocity theorem is verified. Friends, now let us consider simple but tricky example to find Vx in the network shown and verify the reciprocity theorem. To find Vx, I prefer to choose node voltage method. If you observe the network, there are 3 junction nodes 1, 2 and 3. Assuming node 3 as reference, let V1 and V2 be the unknown node voltages assumed as shown. By writing the Kirchhoff's nodal equation for node 1, we get minus 10 plus V1 by 10 plus V1 minus V2 by 4 plus V1 minus V2 by 4 is equal to 0. By rearranging and solving, we get 12 V1 minus 10 V2 is equal to 200. Let it be equation 1. Similarly, for node 2, we get V2 minus V1 by 4 plus V2 minus V1 by 4 plus V2 by 8 is equal to 0. By rearranging and solving, we get minus 4 V1 plus 5 V2 is equal to 0. Let it be equation 2. By solving the simultaneous balance equations 1 and 2, we get V1 is equal to 50 volts and V2 is equal to 40 volts. But V1 minus Vx minus V2 is equal to 0. So, Vx is equal to V1 minus V2. By substituting for V1 and V2, we get Vx is equal to 10 volts. Now, we arrive at the critical juncture. Note that the current source of 10 amperes is introduced in branch 1 and 2 such that the current direction is towards the positive polarity of Vx. Also, note that 10 ampere current source in the original branch is made 0 by opening it, and polarity of Phi is same as 10 ampere current source direction. Friends, after you have done this carefully, the rest is routine of network solving. Let V1 and V2 be the unknown node voltages of node 1 and 2 respectively as shown. Note V1 is equal to Vy. So, by writing the Kirchhoff's nodal equation for node 1, we get Vy divided by 10 plus Vy minus V2 divided by 4 plus Vy minus V2 divided by 4 minus 10 is equal to 0. By rearranging and solving, we get 12 Vy minus 10 V2 is equal to 200. Let it be equation 1. Similarly, for node 2, we get V2 by 8 plus V2 minus Vy by 4 plus V2 minus Vy by 4 plus 10 is equal to 0. By rearranging and solving, we get minus 4 Vy plus 5 V2 is equal to minus 80. Let it be equation 2. By solving the simultaneous balance equations 1 and 2, we get Vy is equal to 10 volts and V2 is equal to minus 8 volts. Since we find Vx is equal to Vy is equal to 10 volts, the reciprocity theorem is verified. Friends, finally we shall solve another simple but very tricky problem to find Ix and to verify reciprocity theorem for the network shown in figure. By observing the network, you find that the network also contains 3 junction nodes 1, 2 and 3. But in this network, you find that the node voltage of one node is plus 12 with reference to the reference node which we know. So, let V1 be the unknown junction node voltage as shown in figure. By writing the Kirchhoff's nodal equation for node 1, we get V1 minus 12 by 6 plus V1 by 12 plus V1 by 12 is equal to 0. By rearranging and solving it, we get V1 is equal to 6 volts, but Ix is equal to V1 by 12. Substituting the values, we get Ix is equal to 0.5 amperes. Now we arrive at the critical juncture of exchanging the positions of the source and the response. Note that voltage source of 12 volts is introduced such that its polarity will drive current in the direction as of Ix. In the original branch, 12 volt source is forced to 0 by short circuiting it as shown. Note, this short circuit will force the two resistances of 12 ohms to 0, and the direction of Iy is same as the current driven by 12 volt source in the original branch. So, by writing the Kirchhoff's nodal equation for node 1, we get V1 by 6 plus V1 by 12 plus V1 plus 12 divided by 12 is equal to 0. By rearranging and solving, we get V1 is equal to minus 3 volts. Note, V1 by 6 in the equation is the current flowing away from node 1. So, Iy is equal to minus V1 divided by 6. By substituting the values, we get Iy is equal to 0.5 amperes. Since Ix is equal to Iy is equal to 0.5 amperes, the reciprocity theorem is verified. Friends, I hope you have understood the concept of reciprocity clearly. Important skill you have to develop is exchanging the positions of the source and the response correctly. I have explained these aspects clearly and lucidly while solving each numerical example. Friends, I suggest you think and recall the points stated and develop this skill. It's not difficult, friends. So, I hope this tutorial has ignited some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.